Okay, let's just jump right in. Today, we're dissecting a really fascinating piece of electronic engineering, the fixed bias circuit. If you look at this thing on paper, the equations balance beautifully. The logic seems absolutely airtight. But as we're going to see in this explainer of the source notes, this seemingly perfect setup harbors a literal, fatal flaw that makes it practically useless in the real world. So we're going to walk through the exact diagrams that illustrate this whole deception step by step. Right, so here's our starting point, the basic fixed bias common emitter or CE amplifier circuit. Looking at the source notes, you can see the layout. We've got our transistor right there in the center, a DC power supply, that's the plus VCC at the top, and a couple of resistors, RB on the base and RC on the collector. You'll also notice an AC input signal coming in on the left and our output going out on the right. Basically, this is the blueprint. But before we get into why it fails so spectacularly, let's quickly review what it's actually supposed to do. First things first, note that this setup acts as an inverter amplifier. As the notes point out, it creates a complete 180-degree phase shift. What does that actually mean for our signal? Well, it means when you feed a positive input half cycle into the circuit, the whole thing gets flipped upside down, giving you a negative output half cycle. It's amplified, sure. The wave is much larger, but it's a total mirror image of the input. Now here's the absolutely crucial part. Before we can pass that AC signal through and amplify it, we have to establish our DC baseline. It's exactly like setting the idle speed of a car engine before you step on the gas. I mean, if your engine isn't idling smoothly, hitting the accelerator isn't going to give you a smooth ride, right? It's probably just going to stall. In our circuit, the DC bias gives us that steady, stable idle state, so the AC signal actually has a clean baseline to swing up and down from. So to figure out our idle state, we have to look exclusively at the DC and just totally ignore the AC. And to do that, we follow two strict rules from the notes. Step 1. We rely on our coupling capacitors, those are labeled C1 and C2, to isolate the DC and AC signals. Step 2. For the actual DC analysis, we treat those capacitors as completely open paths. Just imagine physically snipping the wires where C1 and C2 are. The AC signal is blocked from entering, the output is blocked from leaving, and we are left with just that core, idle DC circuit. Okay, so with the capacitors acting as open circuits, our next move is applying Kirchhoff's voltage law, or KVL. This helps us figure out exactly what voltages and currents are still running through there. The circuit simplifies beautifully here. We can clearly trace the paths, the loops, from the power supply at the top all the way down to the ground at the bottom. And KVL simply tells us that all the voltage drops around one of these closed loops have to equal the total supplied voltage. Let's tackle the left side of the circuit first, what we call the base emitter loop. Starting from the top, we've got our supply voltage, VCC. Now, as the current travels down, it drops across the base resistor, giving us IB times RB. Then it drops across the transistor's base emitter junction, which is VBE. So VCC equals IB times RB plus VBE. With just a little bit of basic algebra from the notes, we isolate the base current, and we get IB equals VCC minus VBE all divided by RB. Honestly, it's a super clean, elegant equation. And here is the really crucial point. Once we know that base current, finding our main collector current, IC, is incredibly simple. We literally just multiply IB by the transistor's beta value. Beta is essentially the amplification factor. You feed this tiny trickle of current into the base, you multiply it by beta, and bam, it allows a massive rush of current to flow through the collector. Everything hinges entirely on that initial IB calculation. All right, moving over to the right side of the diagram, the collector-emitter loop. We just use Kirchhoff's voltage law one more time. We start again at the supply, VCC. The voltage drops across the collector resistor, that's IC times RC, and then drops across the transistor itself, from collector to emitter, giving us VCE. So VCC equals IC times RC plus VCE. If we rearrange that to find the voltage across the transistor, we get VCE equals VCC minus IC times RC. Okay, take a breath. Look at what we've just accomplished. We solved both the left and right loops. We know the currents, we know the voltages, the math works out perfectly, right? It feels like a total success. But here is where we really have to ask the hard question. Is this actually a good circuit design? I mean, does this mathematical perfection on paper actually survive contact with reality? Well, to answer that, we have to introduce a new metric from the notes, called the stability factor, denoted by a capital S. Honestly, you can think of S as the villain in our perfect mathematical story. It measures how well the circuit handles changes, specifically temperature changes that mess with the transistor's internal properties. For a good, reliable design, the source notes explicitly state that S must be kept to an absolute minimum. We want this number as low as humanly possible. If we look closely at the formula for S provided in the notes, we can see exactly how it's calculated. It's a fraction, 1 plus beta, divided by 1 minus beta, multiplied by the derivative of the base current with respect to the collector current. Now, I know that sounds like a massive mouthful, but don't let the calculus intimidate you. The entire fate of this circuit relies heavily on just one specific piece of that puzzle: how the base current changes when the collector current changes. Now, think back a few minutes to when we calculated IB. The equation was IB equals VCC minus VBE divided by RB. Do you notice what is completely missing from that equation? IC, it's not there. The base current in this fixed bias setup is entirely independent of the collector current. And because our earlier equation for IB didn't contain IC at all, differentiating it with respect to IC results in a big, fat 0. The rate of change is absolutely nothing. And guys, this is exactly where the math suddenly turns against us. When we take that 0 and plug it back into our complex fraction for the stability factor, the entire bottom half of the equation simplifies to just 1 minus 0. The denominator basically disappears entirely. Our massive, complex stability factor formula collapses all the way down to a deceptively simple equation: S equals 1 plus beta. So here comes the devastating plot twist. What is beta typically? Well, according to our source material, the standard beta values for these common transistors range anywhere from 100 to 150. Yeah, that is not a small number. Remember our golden rule for circuit design: S must be minimized. But if S equals 1 plus beta, and beta is, say, 150, our stability factor is 151. An S value over 100 means that any slight increase in temperature will cause the current to spike, which increases the temperature even further, which spikes the current again. It's a vicious cycle. Thermal runaway is virtually guaranteed. And this leads the author of our notes to the definitive, underlined conclusion: fixed bias is not suitable for biasing this. This gives poor stability. The perfect math essentially created a totally unstable reality. So we've just systematically proved, using the very equations that built it, that this circuit is fundamentally flawed. It simply cannot survive the real world. But this points us directly to a lingering question from the original source notes. If fixed bias is a guaranteed failure, how exactly does the alternative, voltage divider bias, fix this massive stability crisis? Well, that is the puzzle for you to explore next time.